Welcome back, everybody. This is our video solution to problem 5 from quiz 4, and we're back to Laplace transforms. Here, we're going to compute a Laplace transform using a table, right? This should be pretty straightforward. The table is given. The one thing that isn't given in the table, but which you do have to know about the Laplace transform, is that it's linear, which means if I have the Laplace transform of two functions added together, right? So the Laplace transform of a sum, that's going to be the same thing as taking the sum of the transforms. The other thing is if we have a constant, so this so-called homogeneity property, if I have a constant times a function and I take that Laplace transform, that's going to be the same thing as multiplying the constant by the Laplace transform of f. Right? So we're going to be using that repeatedly as we try to compute the Laplace transform of this nutty function, right? It looks absolutely insane, right? We certainly don't want to go back to the definition to do this, right? Especially when we already have a table. So we want to use these properties first to break this up. It's going to let me pull out these constants and break this up into individual sums. So the first one, I can pull out the 3. I cannot pull out the t squared. T squared is not a constant, right? This c here is a constant value. Can't use a variable value like t. So I have the 3 times the Laplace transform of t squared e to the 4t. All right, then I can do minus 4 times the Laplace transform of sine of 9t. Okay, now a plus 2/7 times the Laplace transform of the hyperbolic cosine of 3t. And finally, hey, no constant to pull out here, the Laplace transform of t to the 99th power. So I've taken one huge absurd problem and broken it up into 4 problems whose answers I should in principle be able to get from this table. All right, let's give it a try. So this first piece, one of the temptations is to break this up and say, oh, this is Laplace of t squared times the Laplace of e to the 4t. This doesn't work. The Laplace of a product does not equal the product of the Laplace transforms. Okay, this is just not a true statement. All right. And it's not surprising because the Laplace transform is defined in terms of an integral. And the integral of a product is not the product of the integrals. And that shouldn't be surprising because the integral is just a reverse operation, right, for doing the derivative. And the derivative of a product is not the product of the derivatives. It's why you have the product rule, right? You just know things are going to be more complicated. In fact, there is a way of trying to compare the Laplace of f and times the Laplace of g with the Laplace of something, but it's called the convolution of f and g. All right, so this is a different topic. Well, what can we do here? Well, we look to our table. And line 2 of the table tells us what to do when we have the Laplace transform of some function of t, which, hey, we do. We have a t squared, times an exponential. And what it says to do is you take, well, what is this big F? Well, we read the instructions. It says that big F is just the Laplace transform of f. Okay. So I would just take the Laplace transform of my f, which in this case is t squared, and then evaluate it at s minus a, where a is this number in the exponential that I multiply by t. So in this case, my a would be 4. So what do I need here? I have 3 times the Laplace transform of t squared, and then I'm going to have to evaluate this at s minus 4. Okay, well, I need to know the Laplace transform of t squared. But again, we have a table. It tells us what to do when we have the Laplace transform of t to the n, right? N here being some non-negative integer. We're going to take n factorial and divide it by s to the n plus 1. So in this case, my n is 2. So I'm going to get 2 factorial. Okay, so 2 factorial, which is just 2, over s to the 2 plus 1. That's s cubed. Now, instead of the s, though, I want s minus 4. So I do s minus 4 cubed. And there we go. There's the Laplace transform of t squared times e to the 4t. It's just going to be 2 factorial, or 2 over s minus 4 cubed. All right, so 2 over s minus 4 cubed. Okay, of course, there's this 3 hanging around. Fine. Now we get to move on to the next one. So we have minus 4 times the Laplace transform of sine of 9t. Ooh, is that in our table? Hey, look at that. We got it. So what do I need here? I have sine of, okay, instead of at, I have 9t. Well, this tells me that the 9 goes in the numerator over s squared plus 9 squared. All right, or if you like, s squared plus 81. Hey, that's it. That's all there is. Okay, so we go to the next summand. We have plus 2 over 7 times the Laplace transform of the hyperbolic cosine of 3t. Hey, that's right in the table again. There we go. Don't even have to know what the hyperbolic cosine is, right? We just know we have it in a table. How beautiful is that? So we're going to get s over s squared minus, okay, I need a squared. What was my a? Well, hyperbolic cosine of 3t. So my a is 3, so this will be 3 squared, or if you prefer, 9. And then finally, we have the Laplace transform of t to the 99th power. And hey, we do go right back to the top line here. We already know what happens. You're going to take, well, t to the 99, so my n is 99. So I get plus, okay, 99 factorial divided by s to the 99 plus 1, s to the 100. I am not going to multiply out 99 factorial. Okay, I'm going to leave it just like that. All right. Using the Laplace transform has a couple of subtleties to it. You have to understand these linearity properties, okay, which you were proving on the homework. All right. You also need to be able to recognize in particular situations like this, where this is of course using the first shifting theorem, where I have some function times an exponential, and then recognize, right, my t squared is the function, and this f means take the Laplace of that, just that function, and then this of s minus a means replace my s with s minus a. Okay, so you do have to do that little recognition of what does this variable correspond to, right, from the formula, right, or in the table into what we're actually given. Okay, but otherwise, once you get that down, this should be a reasonably straightforward process. The beauty of it is, of course, you don't have to compute anything with an integral. You're just using the work you've already done. And how mathematical is that, right? Reduce a problem you don't know into one you already do.